we'll start with the webinar. So my name is Erkki Lamminen, and I'm going to be talking about high temperature aerosol measurements. Here are the contents of the presentation. I'll discuss briefly what are some of the purposes of doing high temperature aerosol measurements. Then we'll go through the LP Plus product family, a little bit about the specifications and operating principles, and specifically we'll take a look at the high temperature ELPI Plus. And then we'll get to the real meat of the webinar, which is to look at applications at various temperatures, starting from very high extreme temperatures, certain applications in that range, then high and let's say elevated temperatures or a little bit lower temperature measurements. So that's what we'll be covering. Now, first of all, the purpose of high temperature aerosol measurements. If we are talking about measurements from combustion sources, whether it's a small fireplace or a power plant, a vehicle engine, or anything else as a typical combustion source, the purpose of doing measurements at high temperature or to use high temperature sampling is to avoid unwanted sample transformation during cooling of the sample. So what happens during the cooling process is that if just the temperature of a sample from a combustion source is allowed to cool down, you get condensation of volatile species and water. They may condensate on the existing particles or on the sampling line walls, or they may nucleate, generating high concentrations of very small particles. Now, typically this sample transformation through condensation and nucleation is unwanted. And the reason is that the emission regulation, whether it's for a power plant dust emission or vehicle exhaust number concentration measurements, the emission regulations only typically consider primary emissions, the solid particles that are in the sample coming from the combustion source. So typically for a power plant, just regulated sampling, a heated filter holder is used so that the condensables don't condense. Or the other way to avoid condensation is to do dilution, so that we first dilute at an elevated temperature at the sample temperature, which then drops down the concentration of the volatile species, so they do not condense anymore when the sample temperature is subsequently lowered. Another reason to do high or elevated temperature aerosol measurements is to look at the volatility of an aerosol. So if we put an aerosol from ambient temperature and start increasing the temperature of the aerosol, whatever volatile species will evaporate. This has mainly an effect on the mass concentration, because even if the particle doesn't evaporate completely, the number concentration stays the same. But it reduces the mass concentration and it changes the size distribution of an aerosol. So by changing the temperature of an aerosol, you can study which particle sizes, which fractions, which modes are volatile. Now, talking about the ELPI Plus, the electrical low pressure Impactor Plus product family specifications. The LP Plus measures number, mass, and lung deposited surface area, size distribution, and concentration. It can do it in real time up to 10 Hertz, so you get 10 size distributions per second. We measure a wide size range from 6 nanometers up to 10 microns, and we have, depending, we can measure either 14 size fractions or we can use inversion calculation to get even higher numbers of size fractionation from the measurement. We do collect the particles in the measurement. Typically, what we use are sintered plates that allow us to do, like from the ambient, to do months of measurements continuously. Or we can use what we call analysis plates that give you the possibility of doing subsequent chemical analysis of the samples. Now, one of the key things I'll be talking about today is the high temperature LP+ that allows us to do direct measurement from up to 180 degrees Celsius. We'll take a look at that in the upcoming slides. So we have a wide dynamic range from low to high concentrations. Due to the measurement principle of the instrument, we can not only measure the size distribution and concentration of aerosols, but we can also analyze if the aerosol is already charged. We can also do charge per particle measurements with the instrument. The calculation routine is fully transparent for both regular measurement and the high resolution measurement through inversion. It's fully transparent how we do the calculation to get the results. If we take a quick look at the LP+ operating principle, we use a vacuum pump to get a flow of 10 liters per minute through our measurement column. And in our measurement column, we first have a corona charger, or a unipolar diode charger, as we like to call it nowadays, rather than a corona charger. But it's simply a tungsten wire to which we apply a high voltage that causes a corona discharge of ions, sort of an ion cloud from the needle to the walls of the charger. So what happens is that when the aerosol goes through this ion cloud, the ions attach onto the particle surfaces through diffusion, and then the particles are positively charged. Larger particles get more charge, and smaller particles, of course, get less charge. It's followed by a small trap field where we collect the ions that are not attached to the particles. Then we have a low pressure impactor, I said 14 stages, where the particles are size classified according to their aerodynamic size onto the different impactor plates. Now, these impactor stages are insulated from one another, so each one acts as an individual Faraday cup. Then we have electrometers connected to each impactor stage, and with these electrometers, we get a real-time signal of the amount of particles that are collected in each stage. So when we know the charging efficiency of the charger and we know the size from the cascade impactor, we can directly get size distribution and concentration of the aerosol. Now, the high temperature LP+ has exactly the same operating principle. The only difference for the high temperature LP+ is that we now have the impactor and the charger, which in the regular LP+ are here. We have the charger and the cascade impactor. And in the high temperature LP+, they are placed inside an external heater. So the operation principle is exactly the same, but now the charger and the impactor are both heated, so we can measure high temperature samples directly with the unit. We'll first discuss some applications related to combustion plants, and we'll start with, by the way, if there are new participants, you can use the Q&A and the chat functions to post any questions, and I'll stop at a few points in the presentation to answer those. So first, regarding the combustion plant related applications, we'll discuss another tool that we can use if we need to go to to even higher temperatures. So as said, with the high temperature LP, we can measure up to 180 degrees Celsius. We also have a unit called an E-diluter Pro. That is a dilution system that is over here. Has a dilution factor of 25 up to 225. The dilution factor is automatically compensated for pressure and temperature effects from the sample and produces enough diluted sample for multiple instruments which can be connected to the diluter outlets. And with this one, we can sample from temperatures up to 600 degrees Celsius. If there's a need to sample from even higher temperatures, we have what we call the Dekati high temperature probe, where that we can use for sample temperatures up to 1200 Celsius. Then we use a cyclone and a cyclone heater here to cut out particles above 10 microns. But we'll first discuss some uses of these high temperature measurements. And typically they would be used in combustion optimization. So measurements directly from the combustion zone with the high temperature probe. So different things can be done with the direct measurements from the combustion zones. It can be used to try to reduce heat exchanger fouling, try to look at what is the loading on the flue gas cleaning devices, optimize for different fuels and different fuel qualities, and look at the operating parameters of a particular boiler. But this combined with the LP would be a full setup for combustion zone measurements. Now, the purpose to do combustion zone measurements is that by using the high temperature probe directly from the combustion zone, we can study whether corrosive species occur in the combustion zone, which is typical, especially with certain lower quality coal, and especially with mixed waste and biomass combustion. So there can be much more potential for production of corrosive species. Now, it's problematic to know whether the corrosive species are formed in the combustion plant if you can't measure it directly. It is affected by the fuel quality and the fuel mixtures, and it's affected especially by temperature. So in high temperatures, there's more propensity for the corrosive species to occur. And for the combustion plant itself, it's always more beneficial to use higher temperatures in the combustion, because then the power plant efficiency is increased. So what the high temperature probe allows the user to do is to measure directly from the combustion zone whether the corrosive species are formed, and then they can use either fuel mixing or use of additives into the combustion to try to reduce corrosion and increase combustion temperatures to get higher power plant efficiency. So we have a question, how long can the high temperature probe stay in the flue gas stream? And is the probe cooled to prevent damages of the high temperature probe itself? Yes, so the probe itself is cooled. It's regulated to roughly from 200 to 400 degrees Celsius. So we drop the temperature in a controlled fashion by diluting it right here, diluting the sample right here at the tip of the probe. We drop the temperature and it basically simulates what happens at the heat exchangers or at the boiler walls. So we drop the temperature. So if there are any potential corrosive species, they will form and they will form as an aerosol, which we can then dilute and measure with the instrumentation. So what we are doing with the high temperature probe is we are simulating what happens at the cooler points of after the combustion has occurred, and then we can measure those corrosive species directly. The probe can stay in the high temperature zone for long periods of time. It has been used for weeks of measurements continuously without any issues. So it can be used for long-term measurements. The most typical use would be to do sort of optimization. So it's not typically used continuously, but try to optimize, for example, the use of additives, or how, for example, coal is added into combustion of biomass, because it can really help reduce the formation of the corrosive species. Then to a little bit lower temperature measurements, when we are talking about measurements after flue gas has been cooled down in the heat exchangers. In the combustion plants, different methods are used to eliminate the dust or the PM from the flue gas, like electrostatic precipitators, wet electrostatic precipitators, baghouse filters, scrubbers, and so forth. Now with the dilution systems, we can measure directly before and after any of these cleaning devices to determine the filtration efficiency, of course, to determine what is the effect of the operational cycles of the cleaning devices, and try to optimize them to be as efficient as possible and to consume as little energy as possible. So as an example of this type of work, here's an article from Energy and Fuels from a study of a fabric filter, a baghouse filter, in real-world conditions in 2 coal-fired fluidicide bed boilers. So they use the electrical low-pressure impactor to measure before and after the flue gas filter to determine the filtration efficiency in 2 different real-time scenarios. Here are the results. As said, the measurements were done in 2 coal-fired plants. One was a circulating fluidicide bed, and the other one was a bubbling fluidicide bed. So the bubbling fluidicide bed results are shown as the blue graph, and then the circulating fluidicide bed is shown as the red graph, both for number and for mass. So here we see before the filter and after the filter, and the same thing for the circulating fluidicide bed before and after. And we can see that in both power plants, very high filtration efficiencies can be reached. So we are talking about from 99 to 99.95% of filtration efficiency. So this shows also the fact that with the LP, we can see very large dynamic ranges. So we are able to measure at the very high concentrations before the filtration system, and then at much lower concentrations to have that resolving power to determine the filtration efficiencies. And then, of course, from these, it can be calculated also the penetration or the fractional penetration as a function of particle size. Another example of an application where the high temperature LP has specifically been used is in studying carbon capture processes. So I'll go through the typical one example of a carbon capture process. So we have flue gas, which has already gone through all of the steps of cleaning in the power plant. So it's as dust-free as possible, as clean as possible in that sense. Still, of course, contains the CO2. It's cooled down to a very low temperature using water, and then run into an adsorber or a scrubber, where the gas is scrubbed with amines, as an example. Different chemicals can be used. So the CO2 is bound to the amines, and then is dropping down in a liquid form, and it goes into a separation unit where the amines and CO2 are reheated, and the CO2 is released and can be captured out of the process. And where the Dekati instruments can be used is that the high temperature LP, because we can measure directly from the scrubber, it can be studied whether any particulates are formed. And the reason why in this case we want to use the high temperature LP for direct measurements is that the humidity is very high, but the concentration is extremely low. So we don't want to dilute, but measure directly from the source. A similar approach can be taken from after other very efficient scrubbers, or for example, wet electrostatic precipitators, to study the efficiency even in situations where the concentration in the output is extremely low. So we can measure it directly with the high temperature LP+. Talking about vehicle related applications, of course, typically engine exhaust measurements, we can use, as can be seen here, the high temperature LP+ measuring directly, in this case, out of an exhaust of a mining vehicle. And the reason why nowadays it's beneficial to be able to measure directly, if you have a new vehicle that fulfills the emissions legislation that are in force currently, the solid particle concentrations are extremely low in the tailpipe. And therefore you would want to avoid dilution as much as possible. The reason why particle size is important or interesting at the moment is that in our upcoming legislation, it's changing from measurement from 23 nanometers down to 10 nanometers. So it's important to know what is the size distribution of the solid particles coming out of the exhaust. And of course, can be used to study fuel and lubricating oil effects, after treatment effects, and especially regeneration effects. When the DPF is regenerating, it's generally generating quite high concentrations of smaller particles. And then of course, after the regeneration effect, the penetration through the DPF is higher than after a few minutes of loading. So it can be used to eliminate those as much as possible. Another aspect of vehicle measurements is the measurement of crankcase or blow-by droplets. So these emissions come from the fact that when we have the pistons in the engine, typically, of course, there would be the cylinder around the piston, and you have the high pressure gas during the combustion phase, and some of that gas will leak through or by the side of the cylinder sealant rings and go into the crankcase as oil droplets and some soot droplets. So with the high temperature LP, we can measure directly once again the crankcase gas and see the filtration efficiency of the filter devices in the vehicle that are then used to remove those oil particles. So it's basically filtration measurements, but in a little bit more difficult conditions, since we have somewhat high temperature, and then both high and low concentrations, whether it's from before or after the filtration device. The last application which is vehicle related is for the brake wear measurements, where the high temperature, the LP can be used otherwise, of course, for the brake wear particulate measurements, but specifically for the high temperature LP can be used to measure the volatility of the particles produced from the brakes, or most likely from the brake pads, because a number of different materials are used in the brake pads, and some of them are more volatile and some of them are less volatile. So the high temperature LP can be used to directly measure the emissions from braking, and also then to see whether those particulates are volatile or not. The reason why this is an interesting thing to study at the moment is that the legislation is not yet set whether there will be an aim to measure only what would be called solid particles, or whether the more volatile particles would be included in the emissions as well. Moving on to other applications now related to air quality. And there is quite a specific interest to do high temperature measurements also related to air quality. And the interest here is to look at what is, once again, volatile in the atmosphere and what is the solid fraction. And the way that this sort of a study can be done is I have an example and some data. We did long ambient measurements with this type of a setup where we have a PM10 inlet going into a measurement station. We use a Nafion dryer to remove the particle-bound water, to remove the humidity from the sample. And then we use two LP units. One is measuring at ambient temperature, and then we have a high temperature LP with a heated sampling line to measure only the solid particles or the primary emissions. So this LP plus measures whatever is in the ambient minus humidity, and this LP plus is measuring only the solid fractions. So the reason why this is interesting is we know that most of the ambient aerosol is actually formed in the atmosphere through either secondary inorganic or secondary organic aerosol formation through with all reactions with ozone and sunlight and so forth. So this allows us to see a little bit of what is the fraction of the solid aerosol and what is the fraction of the volatile aerosol. And we evaluated this for specifically for PM2.5. So here we have a short sample of the data. So here we have PM2.5 real-time measurements where we have the solid and the volatile fraction here. And then with the blue line and then with the orange line, we have just the solid fraction, or let's say what evaporates in 180 degrees Celsius is removed from this result. And we can see that depending on the time of the day or depending on the aerosol, there can be either rather large differences, a lot of volatiles in the ambient aerosol, or in some cases where we clearly have an emission, a shorter time scale emission of solid particulates, then it doesn't really, there's not a much of a difference between the readings from the two units. And we'll take a look at one specific point of this data. And especially looking at the size distribution. So here we have total PM2.5 emission, or total PM2.5 in the ambient, the size distribution, and the mass median is at 782 nanometers. But then the histograms are drawn on the same scale to show you the difference between what is the total and what is the non-volatiles. So here, for the solid particulates, the mass median is much smaller. So most of this stuff is formed in the atmosphere, and we have much less in terms of PM2.5 when we remove the secondary formed aerosol. And the reason why this is of course interesting is that most of the emission regulations are focusing on this fraction. When we talk about reducing the emissions from vehicles, or what are the emissions from, let's say, combustion sources like power plants, it's all focused just on the solid fraction. So it's a fairly small portion. At some points, it's a fairly small portion of the total PM2.5 in the atmosphere. Then as the last example, there's of course health-related applications, whether it's transmission of viruses, measurement of vaping devices, looking at like welding emissions as an example. So of course, one clear application is to look at volatility, especially in the case of electronic cigarettes, and also if there is an occupational health concern, to look at how the aerosols behave at different temperatures. But there is another thing that we can do with the high temperature LP related to all of these applications, and it is the simulation of the human lung conditions, because we can accurately control the measurement or the measurement column temperature, so we can put it at very similar conditions or to a human lung, meaning we could be at 36 up to 42 degrees Celsius and very close to 100% relative humidity, which could be arranged with the high temperature LP. Of course, the high temperature LP itself only provides the temperature, and then the sample would need to be humidified up to a higher relative humidity to reach similar conditions which are really there in the human lungs or in the human respiratory system. So then we could much better understand, when we have different aerosols that might come from different occupational health related sources, whether those aerosols are hydrophilic or whether they are hydrophobic. If they start to grow in size very quickly, they might end up in a different place in the lungs than if they don't. And also, of course, in other sense, if you have aerosols that are very sensitive to temperature, to really understand how even the human body temperature may affect the size and then the deposition of the aerosol. Now, of course, here we do have the benefit that when we can measure a wide size range with the high temperature LP, we can really study what is the portion of the particles that reach the alveoli of the lungs, and which are the proportions that don't even make it, let's say, through the mouth and throat or the nose. So you can have a thorough understanding of where the aerosol would end up in the lungs. Coming back to the setting the 100% relative humidity, it can be actually done with this, what we use here for drying the aerosol. The Nafion material can be also used to humidify an aerosol by providing air at a specific humidity into the Nafion system. We can actually adjust the humidity of the sample itself. So that would be one example of how to adjust the relative humidity of the sample. As sort of final points, the high temperature LP data, whether we consider automotive emissions or whether we consider combustion plant measurements, we're in a good agreement with reference methods or like ambient PM 2.5 measurements. The only thing that you need to make sure when you're comparing different measurement methods is that you are measuring the same thing, and especially when we are dealing with high temperature measurements. Let's say for combustion sources, if you are comparing to heated filter measurements for mass measurement, then of course you should also remove the volatiles from the source. Another thing is, of course, then for filter measurements, is there any sort of pre-cut in the reference method, or is it sort of a total particulate measurement? So if with the other instrument you are measuring PM10, and with the filter you are measuring total suspended particles, the results can be quite different. Also in the ambient measurements, like as said, here we used the Nafion dryer for the ambient measurements, and it's useful to use a dryer because for the reference measurements, the filters are typically desiccated to remove particle-bound water. So in that sense, we get a similar result compared to reference methods when we also remove the water in ambient measurements. And the reason why really the LP Plus instrument is used is that the reference methods, whether it's a filter measurement or other reference methods like for let's say photometer measurements for filtration efficiency measurements, they are usually too slow or laborious for research and develop purposes or for optimization of a process. So the main reason to use the LP Plus family products is to speed up research and optimization, and also then to provide information not available with other methods, like the charge measurement that we discussed briefly, so that if you were studying, let's say, an electrostatic precipitator or any other air cleaning device that uses electric precipitation, you can study it much more thoroughly when you can also do charge measurements or the collection of the samples to do further chemical analysis. But that would be the last point from me, and I'd be happy to take any questions or comments if there are any from the attendees. I don't see any at the moment. I'm going to wait for a little while longer. And at this point, I would really like to thank you for participating to the webinar. And hopefully you found some of the information useful for you. I'd like to thank you very much for participating.